Previously, we learned about inertia, and today we want to learn about rotational inertia, or what is also known as moment of inertia. These two terms are interchangeable and equivalent. So before we start, pause the video and tell me what you know about inertia. Write down everything you can think of regarding inertia, and then see if you already know something about rotational inertia. So pause for a minute and write down, think about and write down everything you know about those two terms. Okay, this is what you should have written down. Recall that inertia is resistance to change in velocity or resistance to acceleration, and that mass is a measure of an object's inertia. It's directly proportional to the mass of the object. It's actually equal to the mass of the object. And so similarly, rotational inertia will be resistance to rotation, resistance to change in angular speed, or resistance to angular acceleration, which is a change in angular speed. And the rotation of an object depends not only on its mass, but the placement of the mass, as I'll show you in the following examples. Okay, so let's see if I can shrink this down to create some space. Put it over here. And let's look at three different situations. Let's take a bar of, in this case, let's imagine it's thin and the bar is of negligible mass, and the bar is 1 meter long, and we take slugs or masses that are 1 kilogram, and we place them, attach them to the bar. Just imagine they have holes in them. And I place the masses here, place the masses here. These are supposed to be identical. They don't look identical, and then place them here. So easy to imagine, if you grab these 3 bars at the center with your hand and twist it back and forth, same with this one, that they'll all feel differently, even though they all weigh or have a mass of 2 kilograms. Remember, we're ignoring the mass of the bar. So they all have, the 3 objects have the same inertia, but they have different moments of inertia. And the way we calculate how much inertia this has is we use the equation that the moment of inertia of a point mass, a mass that's small, and we can consider these relatively small, is mr squared. So I want you to pause the video and calculate the rotational inertia of each of these 3 bars. Let me give you some information first. The mass of each mass is 1 kilogram. The mass of the bar is negligible, and the position on the bar for this mass is 40 centimeters. The length of the bar, it's a meter thick, or it's a meter long, 1 meter. So these 2 masses are placed at 40 and 60 centimeters. The next 2 are placed at 25 and 75. Let me put the units in here. Centimeters, centimeters, centimeters. And the last 2 are at 0 centimeter mark and the 100 centimeter mark. Okay, you can now pause the video and calculate the rotational inertia about an axis at the 50 centimeter mark on each bar. So imagine we put an axis through the center of the bar. Calculate what the rotational inertia will be for these three apparatuses. Let's give them names. Let's call this situation A, B, and C. So pause the video and see if you can do that. Now you can compare what you did to what I did. First of all, let's create some space. Shrinking this and putting it up here. And then we'll say IA equals I of mass 1 plus I of, plus I of mass 2. And it'll be the same for all of those. So in this case, and we would have for I1, M1, R1 plus R1 squared plus M2, R2 squared. But since the masses are the same and the distance is the same, we could just rewrite this as 2mr squared. That would be equal to 2 times the 1 kilogram for the mass, times the r. Notice the r in this situation is going to be 10 centimeters, so I'm going to put it in meters, 0.1 meters. That has to be squared, and so we end up with an IA, which is 0.02 kilogram meters squared. Okay, now if we want to do the next one, we can put this one away, and we're going to do the same thing again, only the numbers will be different. In this case, IB will be equal to the same thing, M1 R1 squared plus M2 R2 squared, but since they're the same, we can skip ahead, say IB equals 2 M1, well, we're dropping the 1, MR squared. And so that's going to be 2 times 1 kilogram. And in this case, times 0.25 meters. Ran out of space here. Squared. So IB equals 0.125 kilogram meters squared. So you can see that this one is quite a bit bigger than that one. And that's because the R gets squared. So as we move the masses along the bar, the rotational inertia goes up very quickly. And just shortcutting the last part, let's put this one away. We would get that IC is going to be 2 times 1 kilogram times 0.5 meters squared, or IC equals 0.50 kilogram meters squared. And you might notice that the result of this one is 4 times bigger than that result, because the masses in this case are 50 centimeters instead of, so it's twice as far away. The inertia goes up by 4 times because of the R squared.